So today I want to continue with this universal relation composed with parity. So last time we actually outlined a lower bound for the simple universal relation composed with parity, and then we showed that this is something like m minus order square root m plus 2 log n minus of 1. So the main idea was to so uh, to design the first stage we gave, so this is uh, first stage which was m minus square root m bits, and here the adversarial strategy was to give the same matrix x to both Alice and Bob, and we chose a transcript pi such that these fraction of, so let me call this delta, so this fraction of total number of matrices were consistent with pi, so that so if you give any of these matrices, the first stage transcriptive would be pi. I think we call it pi 1. And then to do this cleanup, to move on to the second stage, we looked at this graph where we, on the right hand side, we had this set of matrices that were consistent with pi. Let's call it x pi 1. And on the right hand side, we had this pair of matrices z0, z1. These were defined in a particular way so that um, by sampling neighbors of this right hand side, we get what inputs for the second stage. So in particular, they were defined as follows. So z0, z1 is two m by n matrices such that all the rows of z0 has parity 0. So if you take parity of any of the rows of z0, it's parity 0, and all the rows of z1 were parity 1. Not only that, we wanted like any pair of rows here to be a hard instance of parity. So when we proved the lower bound for parity, we used an information theoretic argument where the Kashmir-Wigderson game had only one solution, and this was done by choosing setting yn to be xn except one bit is flipped. So it's only one index where so let me call this ein. So it's one specific index in where both of them differ, and no in every other place they are the same. And to continue on the second stage, the first thing we argued is that uh, because we did not remove it, so in the first stage what we did was to prune some matrices out of this picture. So initially we had 2 to the mn matrices, and by choosing pi 1 we prune out this fraction of them, but we have all the possible edges. So a matrix is once a matrix survives this pruning, it has all the possible neighbors on its right hand side, and the possible neighbors, so the neighborhood relation was this following. So x is adjacent to z0, z1 if x can be constructed from z0, z1 by choosing the appropriate row. So what does that mean? So given a row of x, so x is a bunch of rows, right? X1 to xn, sorry, xm. So based on the parity of this row, so let's say this row has parity 0, then it should be that z0's first row should be x1, and let's say this is parity 1, x2 is parity 1, then z1's second row should be x2, so on and so forth. So basically like x, so based on the parity of x, you get like a partial picture of what z should be, and this z0, z1 should be consistent with this partial picture. And in this partial picture, for every row you get either the z0 part or the z1 part, but not both. Okay, so now the possibilities, the number of neighbors of x were just the number of ways to fill in this partial information. So once you have one of these rows, the corresponding rows has to differ in exactly one bit. The number of possibilities of filling in this partial row was exactly n. So that was choosing which bit you're going to flip of this particular row to get n, the corresponding row. So then there are m such rows, and all of these choices are independent. So we showed that the degree of x was something exactly n to the m. Okay, and so this gave us a graph where we had degree something like n to the m. But the point to note is that we don't have any minimum degree guarantees on z0 z1. All we know is some average degree guarantees. Okay, so we showed that the average degree is something like on the right hand side is something like 2 to the delta, and we wanted to prune out certain fraction of edges, not too many, so that this is also the min degree on the right. And after this pruning, we ensured that every matrix on the right hand side had degree at least n to the m by 4, and every matrix on the so every pair on the on the left hand side had a degree n to the m by 4, and everything on the right hand side had a degree at least 2. And we chose the second stage to be like you choose uniformly at random one of these matrices on the left hand side, and then you choose a neighbor z0 z1 uniformly at random. And then once you choose a neighbor, such a neighbor, yes, so that neighbor should, like z0 z1 should have at least one other matrix adjacent to it which is other than x, because its min degree is 2, and we chose that to be y, and we ran the second stage on x comma y. And the main idea here was that because so in the second stage we wanted to make sure that so what are they trying to solve? They're trying to solve the Kashmir-Wigderson game associated with parity on one of the rows. So in every row on these pair of matrices x and y, because they can created from z0 z1, so the following condition happens. So for every uh, I in m, so either xi is equal to yi, this could happen, okay, or xi is equal to yi parity some eij. So there's some unique index ij in n where xi and yi differ. So either the rows are the same or they are different. But since x and y are different, we know that at least one of them, one of the rows are different. So then the goal of Alice and Bob is to focus on one of the rows. I don't know how, but focus on one of the rows and figure out what is the value of ij. So the only and possible answers to the final Kashmir-Wigderson game are of the form I comma ij for a specific row where this happens. So the second condition happens, and to figure that out, we realize that okay, whatever be the min entropy of this ij given this x, the players have to spend twice that much of amount of communication. So in particular, if this is going to be the answer, Alice has to learn this ij, so that will take h infinity of ij amount of communication, and Bob will have to take learn ij, so this will also take another h infinity of ij. So the total communication has to be twice h infinity of ij, and we argued that the min entropy of ij for any particular row is going to be at least log n minus a constant. So this would prove that the second round has to be 2 log n minus of 1. So this has to be 2 log n minus of 1. But how did we get this min entropy guarantee? We didn't have to do this kind of classification into revealed rows or unrevealed rows because of the the min degree guarantee of a particular x. So what did we have? So at the end of all this cleanup, a particular x had hmm, n to the m by 4 z0 z1 pairs adjacent to it. So now we can use this to analyze the min degree of I. So you're given x, and the way we explain how we sample y, and we want to understand what is the min entropy of ij for any row I in M for these two pairs of matrices. So what is ij? Ij is this unique entry where they differ, if at all they differ. It need not be, I mean, they need not differ on this index, but this is the potential index where they could differ. So an easier way to think about it is like once you give x, you get a particular z0 z1 by choosing these positions I1 to im, where so let's say this matrix x is like this one particular matrix 1 1 0 1 1 1. So what does it tell you? So any so this is X for any z0 z1 to be adjacent to it. So this row has parity 1. So the z1 1 should be 0 1 0. So we have no control over z0. Z0 could be anything, and this row has parity 0. So the z0 2 row should be this, and this could be anything. So similarly, this could be anything. This has to be 1 1 1. So to describe a z0 z1 that is in the neighborhood of a particular X, all you have to describe is this so for every unknown row in either z0 or z1, you have to describe the index where this row would differ from this row. So for example, so by giving I1, I2 and I3 here, you completely describe what is z0 z1 adjacent to X. Okay, so this is very important. So instead of thinking of this edge as this filling in, we'll think of this as this pair of indices where X and Y could differ. So why is that? So if we are sampling, so let's say we sample this edge. So to sample Y, we first uniformly sample a neighbor of X. So let's say we sample this neighbor, and then we sample an Y that is adjacent to this Z0 C1 pair. So then for every row, the potential in entry ij where X and Y differ is the ij in which z0s, the corresponding row in z0 and z1 differ, right? So for example, if in this case, if X is adjacent to z0 z1 by I1 I2 I3, if you sample another Y in the neighborhood of this particular z0 z1, x1 and y1 can only differ in I1, x2 and y2 can only differ in I2, and x3 and y3 can only differ in I3. It need not differ, uh, right? It could be that maybe x1 and y1 are the same, but so for example, I can think of a different y, which is let's say 0 1 0 1 1 0, and let's say this I3 is set to be 3, so this is 1 1 0, so I can set this to be 1 1 0. So this y is in the neighborhood of 0 0 c1. So all we know is that, okay, it could be that some of the rows of x and y are the same, but if any row differs, it differs in this particular position. Okay, so to know the mean entropy of this potential index, it's just to look, it's enough to look at the mean entropy of ij in the neighborhood, in the uniform neighborhood of X. So the way we sample Y, it's equivalent to sampling one of these z0s z1. Okay, you might wonder that there is more mean entropy left because a z0 z1 we argued that has mean degree 2, but it could have more, but we can always assume that it's exactly 2. We can discard the other neighbors. So once you choose X and once you choose a z0 z1, you can immediately fix Y. So the mean entropy of this particular index is completely decided by how many such tuples you see in the neighborhood of X. Okay, and the number of such tuples by so number of I1 to Im in the neighborhood of any X was what? So this is the mean degree of X, right? So mean degree of this X by 1 after cleanup. And we argued that this was at least the average degree, or which was also the mean degree earlier, by 4. So this is n to the m by 4. So and then the argument was completed by observing that the mean entropies of any of so the mean entropy of I1 to Im collectively is upper bounded by the mean entropies, individual mean entropies summed over all these things. So it could be much smaller by condition, by the chain rule. You have to do certain conditionings, but it cannot be more than the individual mean entropies, right? This could only be smaller than this. J, J, and M. And because this was this was uniform over n to the m by 4. Mean entropy of this as well as the entropy of this was at least the logarithm of this thing. So that is m log n. So this was at least. So by this fact, we know that this is at least m log n by minus 4. And this ensured that, okay, so the sum of these mean entropies should sum up to something like m log n minus 4. The maximum value one of these things can achieve is log n, because what is this? This is an index in 1 to n, and we saw that mean entropy is maximized by the uniform distribution, and over the uniform distribution, the probability of ij is 1 over n, and so hence the maximum mean entropy possible is logarithm of this inverse. So this is log n. So we have m things, all of it, all of them are bounded by log n, and they have to sum up to at least m log n minus 4. So all of them, we can claim, has to be at least log n minus 4. So we can say that for all j in m, this implies that h infinity of ij has to be at least log n minus 4. If not, if even if one of them has a smaller mean entropy than this, the sum cannot be this much. Okay, because the rest of the terms cannot compensate. So even if one of them has, let's say, log n minus 5 and rest have all the maximum possible mean entropy log n, this would only sum up to m log n minus 5. So that's a contradiction. So hence we know that given an x, Alice doesn't know what this ij is. So first thing, so there are two things to consider, right? So first, given x and y, Alice doesn't know if xi is equal to yi, or if xi is equal to yi plus eij. But even if she knows it's different, she doesn't know what this ij is. So this eij, this index ij is, and she has to learn. She has to use mean entropy of ij many bits to learn this. So Alice has to spend log n minus 4 bits to learn this, and Bob has to learn log n minus 4 bits to learn this. So this says, so if they don't learn this index is not completely decided, and by the and the end of the protocol, they would not be able to precisely tell this is the index where they differ. Okay, so we are not even so we are giving this issue for free. Like maybe they figured out that, okay, they do differ on the ith row, but they have to figure out where they differ. So even if they have to figure this one out, they have to spend 2 log n minus 8 bits of communication. Otherwise, this index ij is not completely decided, so there's no one answer I comma ij that they can output. Okay, not decided if second stage is less than 2 log n minus 8, strictly less than this. And this was just basically the argument we use for lower bound of Kashmir-Wigg relation of parity, where we proved that the communication complexity of that is just 2 log n minus of 1. And the main thing is that Bob has to learn this index ij and Alice has to learn this index ij. It's not enough for the one of them to learn. So are there any questions about this argument? Okay. So now I'd like to introduce a more complicated version of this universal relation with parity. And this is somewhat of a so here our life was easy because all of these indices ij had quite high mean entropy. Okay, this is not something we can expect in the other in the case. So what is our final goal? We want to prove that oops, okay, so communication complexity of Kashmir-Wigg relation of f composed with kw parity. So I'll just denote it by just f composed with parity is at least depth of f plus depth of parity minus some slack, right? So we want to build up to this, and in this case we cannot in for technical reasons we cannot get that after the first stage this ij's have really high mean entropy through such a simple argument. So like in the case of universal relation composed with universal relation, or a function composed with a universal relation, we'll have to do a more complicated cleanup where we divide rows into revealed and unrevealed rows based on how much mean entropy has been lost in this index ij. Okay, so to build towards that, and this is quite non-trivial, and to build toward that, we'll first go through a complicated version of universal relation composed with universal relation. So universal relation composed with parity. So what is this going to be? So this is the, so let me just call this complicated version of composed with, sorry, parity. And so in the normal universal relation, what this in the normal version of composed with parity, what do Alice and Bob get? Alice gets X and Bob gets Y, and they're given this extra promise in the promise version. So they compute parity of x1 to xm and compute this vector A. So this vector A is that A1 is parity of this first row, an is parity, am is parity of this mth row, and similarly given Y, Bob would compute a B. Okay, and in the promise version, they're given the promise that A is not equal to B, and that's it, right? And in a non-promise version, if A and B are the same, they can reject. And their goal is to find an index ij such that xij is different from yij. So now I'm not going to change the inputs, but I'm going to give them an extra promise, but only for the first stage. Okay. So here is going to be the thing. So in the first stage, apart from this matrices x, y, so this is the complicated version. So in the simple version, they got these matrices x and y, but in the complicated version, Alice gets a matrix x and Bob gets a matrix y, and they're also and they're also given a bunch of vectors. So it's an m tuple vector I1 to Im. So this is an n to the m, such that they're given the following guarantee only for the first stage. Okay. So for the first m minus delta bits, they can see this vector, and they're given this guarantee that, okay, so for uh, any row j in m, either the following two conditions happen: either xj is equal to yj, so Alice and Bob agree on the jth row, or if they differ, if at all they differ on this particular index. So what does it mean? So xj is equal to, so maybe let me call this I in m just to be consistent. So either xi is equal to yi or xi is equal to yi, but with the okay, so that was not a good idea to call that I. So let me call this j itself. Okay, so let me call this vector j1 to jm. Okay, and for every I in m, we are guaranteed that xi is equal to yi or xi is yi, but it is flipped at e ji. So this is so given an index I, there's a unique index ji which is in 1 to n, right? So this every coordinate here is from 1 to n. So either the rows agree or they differ on this particular index ji. Okay, and not just that. So in the first stage, so they have this additional information. This is a promise problem where they have like essentially two promises. The one promise is from earlier. So if you take the parities and compute A and B, A is different from B. But then there is this additional promise, and this is only for the first m minus delta bits. So there is this vector j1 to jm that they can see, and they're given the guarantee that their inputs either agree on a corresponding row, or they differ only on the position described by this vector j1 to jm. Okay. So now what happens after this is that in the second stage we want to prove a similar lower bound as universal relation composed with parity. So in the first stage we let them communicate m minus delta bits, and in the second stage we want them to communicate 2 log n minus O of 1 bits, and then prove that it would still make an error. And we want to in the second stage, where they are allowed to communicate an additional 2 log n minus O of 1 bits, we'll assume that they can no more see these vectors. Okay, so in the first stage they can look up this vector and figure out where a potential difference could be, and once the first stage is over, we assume that they have no longer access to this. So this is a very strong restriction, because in the traditional two-party communication model, Alice and Bob are unbounded computationally, memory wise, and everything, so they could just write down this j1 to jm and then proceed. But here we don't let them do that, so we assume that they can see this j1 to jm values only in the first stage, and after the first stage they forget what this is. So this might seem like a strange version, but this is to like build up towards the final thing. So f composed with parity would have similarities to this complicated version, and once we describe that, it would make sense why we have this specific restriction only on the first stage. Okay, so now we need to define the first stage transcript. So what are we going to do? So first stage, uh, we are going to consider we're going to give Alice and Bob the same matrix X. So the first stage inputs, don't want them to figure out any differences in their matrices, so we're going to give them the same matrix X, and the vector that this vector J uh, is going to be, so this vector J, it would be any of, so this is just vector J to J1 to Jm, so this can be any value in n to the m. Okay, so it does not matter what j1 to jm are, right? So we want it to satisfy this promise that the inputs that they're given in the first stage, if the row of Alice and Bob differ, they differ only at this position ji, right? But on the set of inputs that the adversary is considering, which is x comma x, there are no rows which are different. So it's vacuously true that for all rows I in M, xi is equal to yi, or xi is equal to yi plus eji, no matter what ji is. Why? Because we are setting x equal to y. So it always, the first condition is turned on and it's true, so we don't even have to worry about the second condition. So the adversary is going to give Alice and Bob the same matrix X. So this can be any matrix in 0, 1 to the m by n. And it's going to give the extra vector that they know in the first stage to be an arbitrary vector from n to the m. Okay. And how are we going to choose the first stage transcript? It is quite similar to how we did it for uh, just a plain universal relation composed with parity. So this is the first stage. So this is the first m minus delta bits. So here also delta is going to be order square root m. Actually O tilde of square root m. But That's not too important at this point. So we have this protocol pi, and we run this on uh, x comma I, so x comma j. So what do I mean by that? So this is a tuple from, so first thing is an m by n matrix. So x is an m by n matrix, and j is a vector of m coordinates, each of which is 1 to n, value in 1 to n. And we give both Alice and Bob the same input. So we give xj to Alice and xj to Bob. Okay. So now, given this input, because this is a deterministic protocol, there is one specific transcript of the first stage that this input would be consistent with, right? So now, given any pair x comma j, I can label it with one of the first stage transcript. So I just run the protocol on this input and see where it ends up. So it ends up in one of these sleeves. So maybe for something else, um, I'd run into this. So for a different, let's say x dash and j dash, it would end up here. So this would be another pi one. So by just running this protocol for first time minus delta, I get a labeling of these xj pairs. Okay. So in the earlier simple uniform universal relation composed with parity, this labeling was only on the matrices. There was no concept of j. So for every x, we got a label, and we chose a label which kept majority of x's. So here we're going to choose a label which would keep majority of these xj pairs. So this, so what is this labeling scheme? So this labeling scheme takes a pair x comma j, and it would output a transcript pi 1 of the first stage. So this labeling is again we'll use a pigeonhole kind of argument. So how many possible xj pairs are there that we consider? It's 2 to the mn. So the number of m by n matrices is 2 to the mn, and the number of these vectors is exactly n to the m. So there are these many xj pairs, and they have to go into 2 to the m minus delta labels. So there exists some pi 1 of the first stage, right? Such that the number of xj pairs supported by this thing in s pi 1 is 2 to the m minus delta of 2 to the mn times n by m. So 2 to the mn times n to the m divided by 2 to the m minus delta. Okay. So this is just the same kind of averaging argument. Now we have to do a cleanup before we can go into the second stage. So to do the cleanup, we'll again think of these inputs using the earlier graph that we were thinking of. So here's the cleanup. So on the right hand side, I would denote by x pi 1 all the matrices x that got the label pi 1. So what does it mean? So a matrix x is in here if there exists a j in n to the m such that x comma j, sorry, x comma j was in s pi 1, right? Mhm. And on the right hand side, we are going to consider again these z0 z1 pairs. Okay. But now remember that we said that this neighborhood relation can be completely captured by a tuple j1 to jm such that x describes half of the rows of the pair z0 z1, and j1 to jm describe where the other row differs from the filled in row. So every edge can equivalently be described by a vector in n to the m, right? This is crucial. So now we only keep, so in the earlier argument, we had all of these possibilities alive. We kept all of them. But here, in the first stage, we are revealing where X and Y could potentially differ. And we only want to keep those J's which are consistent with the transcript that we have chosen. Okay. So it is possible that, okay, so maybe like X had, so for example, X had like two potential neighbors, 1 2 3, and 1 1 3. So in this case, it in this new kind of complicated universal relation, we are not only giving X, but we are also giving this vector. So it is possible that on this matrix and this vector pair, the protocol sends some set of messages pi1, which is like, I don't know, 1 1 0 0 0, and this pair, it choose some other first stage message. So it is possible that, like, based on the first stage message that we choose, so we chose this one, then this edge is not no more there. So the players, by communicating, has ruled out certain pairs of tuples. Okay, but so we only keep the edges such that this edge, so this is some j, so this edge is in the graph only if x comma j is in S pi 1. And what does it mean, x comma j is in X pi 1? So if you run the protocol with x comma x given to both Alice and Bob, and they are given this extra vector j, but they guarantee that their rows differ only on the positions described by this vector, and we run it for m minus delta bits, it would reach pi, right? Just by the definition. So now in this new graph, I want to, like, to continue with the cleanup, we want to understand the degrees on the left and the right. Okay. So in the simple case, the degree on the left hand side was n to the m. Because why was this the case? Because the players were not given this extra information. They could not have ruled it out. Like, I mean, they have no information on J. In fact, they could not figure out what J is because they're given both the same set of matrices. But here, although they are given the same set of matrices, we are telling them in the first stage, look, there's this additional information. I guarantee you that if they are different, they're only going to be different on these coordinates. So thus, giving this information, we are allowing them to prune the edges of this graph. Earlier, they could only prune the vertices of the left side. So the degree on the right hand side could change, but the degree on the left hand side was always n to the m. But here we are allowing them to selectively prune the edges. So if you keep a matrix in X pi 1, it is not clear that all of its neighbors are in there. Okay, but what do we know? So what is the guarantee that we know? We know that S pi 1, we know something about cardinality of S pi 1, right? So let me just redraw this thing. So on here we have X pi 1, which was defined earlier as to be like every x which is in S pi 1 for some j, and then edge relation was 0 z1. We said that this edge can be written as this vector j, which is j1 to jm, and this edge was in the graph only if xj belong to S pi 1. So the number of edges in this graph, right, is exactly equal to cardinality of S pi 1. But the way we chose the first stage transcript, we ensured that this S pi 1 was quite large. So the number of pairs this xj in S pi 1 was the total number of such edges divided by 2 to the m minus delta. So we know that this is at least 2 to the mn times n to the m. This is the total number of edges because there are these many matrices initially, and all of them had these many edges on the right hand side. But in here, we know that maybe not all of them survived, but a huge fraction of them survived. Okay. So now, what can we say about average degree of x? So average degree, so let me call this partition U, and let me call this partition V. So average degree on the U side, so we know that it's at least, so it's exactly equal to the number of edges divided by x pi 1. But I don't know how many matrices are in x pi 1, so I only keep a matrix there if there is at least one vector that is consistent with that matrix that I can give to both the players. So I don't know what is x pi 1, but I know that it's no more than 2 to the nm. So we know, so this is exactly equal, but since x pi 1 is at most 2 to the nm, and I'm dividing with a larger value, I get that this is at least number of edges divided by 2 to the mn. Okay, so and we know that the number of edges is at least this much, so this is at least. Okay, sorry, so this says that we retain at least this fraction of edges. Maybe we retain more, but we know that it's at least this much. So again, we read that this is at least 2 to the mn, 2 to the sorry, n to the m divided by 2 to the m minus delta times 2 to the mn. So this goes, so this is n to the m minus, so in the way to write this would be n is 2 to the log n, so this is 2 to the m log n minus m minus delta, but I'm going to drop the delta, so I'll just write m. So this is at least this much, right? I mean, dividing 2 to the uh, dividing by 2 to the m minus delta gives you a larger number than dividing by 2 to the m. Okay, so this is what we get for the average degree. Okay, and now I want to see whether our earlier argument can work. So the earlier argument said that, so in for the second stage to work, we need the min entropies of this ji's that we see on the neighborhood of x to be very large, right? So earlier we had this thing that h infinity of ij in the neighborhood of x was very large, because what did we know? We know that h infinity of a pair. Okay, so let me not call this ij but ji, the way we are writing it. So for any I in m, we knew that in the neighborhood of x is a bunch of these coordinates j1 to jm, and we look at a particular value of a particular row. The value that the ji took was uniformly at random from, or its min entropy was very large. And the reason that was the case is that if you look at the, if you take any x and you look at the neighborhood, uh, and you look at this tuple collectively, this min entropy was uh, at least, because we are choosing uniformly from the neighborhood of x, was not at least but also equal to log of degree of x. Okay, and earlier our degree was n to the m. In the earlier simple case, this was log n to the m, and so this was m log n. But we, in the cleanup process, we lose some by 4, so we just lose some minus 4, right? So and hence we were able to get that, and since this was upper bounded by the sum of I in m, h infinity of ij, we were able to get that this is at least m log n minus 4. And because all of these values maxed out at log n, we knew that all of them had min entropy log n minus 4. But now we cannot use that argument anymore. Why so? So what is the new min entropy guarantee that we get? So it's the log degree of x. So we don't know what's min degree of x, but we know what's average degree of x. So the best we can hope that is the average degree is also exactly equal to min degree. Although we won't be able to do that, we'll use some minus 4 factor, but let's not worry about that. So in this case, what was our degree? So in the average degree of a matrix on the U side was 2 to the m log n minus m, right? So this was log of 2 to the m log n minus m. So we, instead of getting this minus 4, we'd get minus m. And now m could be much larger than log n, right? So if that is the case, we have no guarantee that all of the rows I have h infinity of ij very high. Let's say m is exactly log n. Okay. In this case, it is possible that maybe h infinity of I1 is 0 and the rest have full possible mean entropy, and they could add up to m log n minus m, right? So if the remaining coordinates, so for all uh, j in m but minus 1, so every row other than the first row, it is possible that maybe they have mean entropy, the maximum possible mean entropy, so that is log n. So it is possible that the sum can be as large as m minus 1 times log n. Okay, so since that is the case, so in the right hand, the left hand side said this is at least m log n minus m, but since we assume that m is equal to log n, so this is equal to m times m minus 1 times log n, right? So m is log n, so in that case this is m minus 1 times log n. So we don't get any guarantee on all the indices ij. So it could be that maybe one of these indices ij has mean entropy 0. So we can't just use a simple sum to say that if you look at the neighborhood of x, this vectors that appear on the neighborhood of x has high mean entropy for every one of the coordinates. So then we need to do a cleanup argument. Okay, so we need to we need to say that, okay, maybe some of these coordinates have very low mean entropy, but then conditioned on so we somehow fix those coordinates, and then conditioned on that fixing, the remaining coordinates have high mean entropy. Okay, so it is possible that not all of them have high mean entropy, and if it is not the case, then we cannot just simply use the earlier argument, because the earlier argument assumed that, like, going into the second stage, any of these coordinates ji where xi and yi could potentially differ had mean entropy at least log n minus 4. So no matter what the row they are trying to solve it on, in the second stage they have to spend log n minus 4 bits of communication, or both on Alice's side and both on and Bob's side. Okay, but here we don't have any such guarantee, so it is possible. So by just a simple calculation that we employed it last time, it is possible that if it is the case that m is quite large, if m is as large as log n, it is possible that one of the coordinates have no mean entropy. Maybe Alice and Bob completely know what j1 is, and in that case, going into the second stage, they don't have to learn. Maybe they solve the second stage on the first row, and don't have to learn j1, and they can solve this second stage without even communicating. So this argument is not going to cut it. So we don't want them to. So it is possible that they've learned quite a lot of information on one of these coordinates, and we don't want them to solve the second stage on these rows where they have lost mean entropy. So we need a complicated cleanup, like in the case of function composed with universal relation. Okay. So the first thing that we are going to do is, okay, so just to summarize, we had this graph. So graph uv, and on this side we have x pi 1, and we knew that the average degree on the left hand side, so we don't know what's min degree, but the average degree is uh, 2 to the m log n minus m. And we didn't think about the right hand side yet, but we'll do that soon. So this is V, this is U. So the first thing what we want to do is like we want to ensure that the min degree on the left hand side is quite large. So we know how to do this using this lemma that I did not prove last time. So we can prove this time. So what I'm going to say is that okay, so this is the general lemma, which says that suppose this is the simplest form of this lemma. Suppose that you have a bipartite graph GUVE, okay, and let's say uh, du be the average degree on the u side and dv be the average degree on the v side, then I want to claim that like we can get a subgraph g dash, right? And then this subgraph, so there exists some subgraph g dash on u dash v dash e dash. So u dash is a subset of u, v dash is a subset of v, e dash is a subset of e, such that uh, this this subgraph is non-empty, and we remove so it contains, so e dash contains some 1 minus epsilon fraction of e, so we retain quite a lot of edges, okay, and then and the average degree we can say that the average degree, the min degree of all the vertices on the right hand side is quite close to the average degree, okay. So and du, so for any x in u dash, so for all x in u dash, the degree of x in u dash, so let me just denote it by this, is at least epsilon times degree of the average degree of u. So we had a graph where we had some kind of average degree guarantee on one side, and we want to get to a new graph which retains most of the edges in the original bipartite graph. But now the vertices on the left hand side has min degree that is comparable to the average degree earlier. And this is a very simple argument. So what do we do? So we look at this graph, GUV. So maybe I can just do this in the last picture itself. So we look at all the, yeah, so let's draw this again. So we have UV. So we know that the average degree on the right is du. So we look at all the vertices on the, sorry, on the left is du, and we look at all the vertices on the left where the degree of this x is strictly smaller than du, sorry, epsilon du. So epsilon is some parameter that we're going to fix. Think of it as something like 1/4 or something. So we look at all the vertices which violate this constraint. So we want to get to a bipartite graph where the min degree is more than epsilon times du. So we'll first look at all the vertices which violate this property. So how many? So one idea is just to simply remove them from this bipartite graph and call the resulting bipartite graph uh, the result of the lemma. So in right, so uh, by this pruning algorithm we would have removed any vertex in u where the a degree of u was smaller than epsilon times du. So by doing this pruning we satisfy this condition, right? So let me call this condition 2. So condition 2 is immediately satisfied just by throwing out vertices like this, okay. So throw out all x's such that degree of x in this original graph is smaller than epsilon du. Now I want to say that this also satisfies condition 1. So condition 1 says that by doing this pruning we all we only throw out some epsilon fraction of the edges in the original bipartite graph. And this is easy to see. Why is that? So for every vertex that we remove, how many edges do we remove? Epsilon du, right? Because we decided to throw out a vertex in this pruning because its degree was uh, epsilon times smaller than average degree. So its degrees, it was most this much. So how many edges do we throw out? It's at most it's the number of x's thrown out times, so the number of edges removed is this times epsilon du. So it's at most this much, right? Number of edges removed. But now we know that number of x's thrown out is, it cannot be more than number of vertices on the right hand side, right? So the number of vertices on the left hand side is this is at most cardinality of u, right? So this tells you that this is at most epsilon times, so I want to rewrite it this way, u times du. But what is u times du? Du was the average degree of vertices on the left hand side, u is the number of vertices on the left hand side. So this is just, so this, because this is the average degree, this is the number of edges, this is the average degree on the left hand side, this is number of edges divided by cardinality of u. So just multiplying by u with average degree, we get back the number of edges. So this is at most epsilon times number of edges, right? So this simple pruning algorithm takes a bipartite graph and make sure that on one side the minimum degree is at least some constant fraction of the average degree, and it retains most of the edges of the graph. Okay, so we first do this pruning. So by doing this pruning, we know that, so we get a new graph where every matrix has at least, so earlier it had 2 to the m log n minus m edges on the right hand side. It has this many neighbors on the right hand side, but now it will have, let's take epsilon to be 1/4, so by 4, so that's like another minus 2, uh, these many edges. And we know that the number of edges in the graph only shrunk by a factor of 3/4. So, and by doing so, number of edges retained is 1 minus 1/4, which is like 3/4. So not number of edges, the fraction of. Okay. So now, so there are quite a lot of, so what is this neighborhood of x? We said that it's completely described by a vector j, which is an n to the m, which tells you which are the potential places where the rows of x and y that we sample at the end could differ in. And now you want to say that this j, this potential place where these rows differ, has high mean entropy. But as we saw that we cannot say that for every coordinate of j, so we want to divide. So given x, so our idea is the following. So given x, we want to uh, divide uh, I in m into two things. So this revealed row, if this h infinity of ij in the neighborhood of x. So when I say condition x, so I'm looking at the various possible values of this ij just in the neighborhood of x. So if this h infinity is much smaller than what we need, so we need something like log n minus O of 1, and if it is much smaller than that, we will call it revealed, and we'll call it unrevealed if it is not revealed. So if the mean entropy is sufficient. And we want to ensure that, and going into the second stage, the players are only allowed to focus on one of the unrevealed rows. Okay, on the revealed rows, this mean entropy could be much smaller than log n minus O of 1, and we have no guarantee how small it is going to be, and so we cannot allow them to solve the KW parity game on one of these rows, because to solve the KW parity game, it's enough to figure out what is ij, and to do that they just need to spend twice the mean entropy of ij. Okay, so we want to somehow force the players to solve the second stage on the unrevealed rows. But before we could even do that, we need an averaging kind of argument to say that we can there are not too many unrevealed, so there are not too many revealed rows. Okay, so how many should there be? So this is one thing to think about. So given any x, we know that the number of different possible j's that it sees, or the min degree of x, is what? It's 2 to the m log n minus m minus 4, but I'm going to ignore that minus 4, so it's at least going to be this much. Okay, so they're going to be these many things. So it is possible that, okay, so if initially this was 2 to the m log n, and in that case the min entropy was the maximum, all the coordinates had min entropy log n, and now we have lost about m bits, like m bits of information, right? So now, so initially we saw j to be any like the j was anything in n to the m, which was n to the m is 2 to the m log n. So initially, like all of these coordinates, ji had maximum min entropy. Now we have lost to the minus m fraction of these coordinates. So the total amount of information that we revealed, so total info on I sorry j1 to jm given this particular x is about m bits. So this is from our intuition that, like, whenever we reduce a set by some 2 to the minus k, that's like equivalent to revealing k bits of information. Okay, and now we want to say that these m bits has to be spread out. It cannot be that on every coordinate the min entropy drop by m bits. So we want to, like, say that this m bits have to be spread out. So we choose a threshold, like a, so first fix a threshold, um, tau, such that, okay, so what does it mean? So a revealed row, so a row is revealed, a row I in m is revealed if h infinity of this ji given this x. So what does it mean? So I'm choosing a j unit. So I first fix this x, so x is fixed to a particular matrix, and now I sample this uniform, so in the, from the neighborhood of x, I sample one neighbor uniformly at random. This would give me a vector in n to the m, and now I look at the value of ji of that particular matrix, the particular vector. So we sample uniformly from the neighborhood of x and then project it down to only the coordinate on I, so the ith coordinate, and we are looking at what is the min entropy of this particular coordinate. Okay, we say that this is revealed if this min entropy is lower than so what is the min entropy that we want to get? It's some log n, so maximum min entropy is log n, and we want to say that it's smaller than log n minus tau. Okay, so this was like in the first case, in the earlier argument of universal relation composed with universal relation, or universal relation function composed with universal relation, where we said that a row of the matrix was revealed if they knew more than tau bits of information. Here we are not talking about the rows of the matrix, because they're not in the universal relation. They were trying to figure out what was the row, right? They want to know if the rows of Alice and Bob were the same, or if they were different, where does the difference happen? Here we in the way we are sampling these inputs, we know that either these rows are the same for Alice and Bob, or they differ at a particular index ji. So the information contained in rows is only ji, right? So we are not measuring how many bits are not known about the rows, because that's not useful for argument. For our argument for parity, we are we are not letting rows of Alice and Bob to be any rows. but we are restricting them to be either these rows are the same or they differ on exactly 1 bit. So we are going to measure information by fixing Alice's input and seeing uh, how much entropy is left in this unique coordinate where Alice could potentially differ from Bob. Okay, but because x had mean degree 2 to the m log n minus m, we know that given any x, the uncertainty so given an x, the uncertainties about these values j1 to jm, and this these coordinates together had m log n bits of information. And because we still have 2 to the m log n minus m of these things, we have revealed at most m bits of information on these coordinates, right? So we want to analyze how many coordinates are there where the amount of information is dropped below tau. So the total amount of this again an averaging argument. We want to use some kind of averaging argument to say that uh, number of revealed coordinates, revealed rows I, such that is at most the total amount of information that you reveal on these tuples, which is this loss factor minus m. So it's the total amount of information divided by tau. This is what we want to do. But now, earlier we measured information with respect to predictability, which measured how many bits they know about a particular row given other rows. But now we are going to measure information relative to mean entropy. Okay, so we need an averaging argument for mean entropy. So here is so there is a simple averaging argument that we can do, but that's not going to work for us. But let's see that one first. So what's the idea here? So we know that, okay, so here is the thing. EIRS style averaging for mean entropy. So what are we going to argue? So we know that so H infinity, so if you take the mean entropy of these coordinates j1 to jm altogether given a particular x matrix x, we know that that mean entropy is m log n minus m, right? Why is that? Because we are sampling uniformly at random from 2 to the m log n minus m of these things. So the mean entropy, because it's a uniform distribution, is just the logarithm of this. Okay. So what is so just to remind you that what was the definition of mean entropy? So mean entropy of a random variable x was just uh, the same definition as the entropy, but instead of expectation we do a minimum over the values small x, such that minimum over this log 1 over probability x equal to x. So when you say that mean entropy is so let's say h infinity of x is at least k, what does that mean? So this means that minimum over all x log 1 over probability of x equal to x is at least k. So this tells you that this this probability cannot be too large, right? So if what does it mean? So minimum over all x log 1 over probability of x equal to x is at least k. So this is equivalent to saying that for any x, so for any x, right? So minimum is this thing. So log of 1 over probability of x equal to x is at least k. So if you take exponential, so this is saying probability of x equal to x is at least 2 to the k. So I'm just taking 2 to the, so logarithm is always with respect to 2. So if I'm taking 2 to the this much, 2 to this much, so log goes away. So this we get this. So then we get that so this is equivalent to saying 1 over 2 to the k is it's an upper bound on probability x equal to x for any x. So this says that if you look at the distribution, it need not, if x was a uniform distribution on 2 to the k things, the probability will be 1 over 2 to the k. But now, mean entropy being k, it doesn't tell you that all of them are 2 to the k, 1 over 2 to the k, but it's saying that any point in the support of this distribution would not have too high a probability. So this says that if you have some lower bound on mean entropy, this then tells you that if you sample according to this distribution, for any particular event, the probability of that event happening is not too large. Okay, so this was equivalent to saying h infinity of x is at least k implies probability of any particular x equal to x is at most 1 over 2 to k. Okay, just to, yeah, so this is what mean entropy guarantee means. So we know, and in here we know that the mean entropy is at least this much. Okay, and then we want to say that so let me erase this part. So we want to say that this loss in mean entropy is distributed across the coordinates of j1 to jm. So the first averaging argument say that there exists some set of bad coordinates, just subset of m, such that h infinity of any so for any uh, row which is not a bad row, so for any row which is not a bad row, for any I in m minus bad, we want to say that if you look at the h infinity of this particular coordinate ji given x, this is at least log n minus tau. So tau is this threshold that we choose. And how would tau related to this bad? And we want to say that based on this threshold, there are not too many bad coordinates. And number of the cardinality of bad rows or revealed rows is at most m minus m by tau. So these are two things what we want to say. So we want to say that the number of revealed rows is not too large, and for every unrevealed row, the mean entropy is very high. But we won't be able to say exactly. So the first argument we won't be able to say for just condition on x. We will also have to condition on setting the bad rows. So you sample this j uniformly random, and we're going to set the bad rows of j to some specific value j bad. Okay, so we can't say just that okay, there are some revealed rows and every unrevealed row has high mean entropy. We can't say that, but we can say that they every unrevealed row has high mean entropy if you fix the revealed rows. If you fix the j for the revealed rows, then we can say this. Okay, and this is not going to be too hard. So we'll see this argument, and then we'll end the lecture for today, and then we'll see the problem with this kind of argument, and we'll need a more complicated averaging argument, which we'll see in the next lecture. So we are trying to prove this theorem, which says that. So let me just copy this. So this is kind of a averaging argument for mean entropy, exactly in the style of the AIRS argument for universal relation that we saw in the couple of lectures earlier. So this is what we want to prove. Okay, so there's some set of bad rows which are not too large, depends on the threshold that you choose for the unrevealed rows, and conditioned on bad rows fixed to some specific coordinates, every other row has high mean entropy. So this is going to be, and how do we prove this? This is going to be a simple algorithm, a cleanup algorithm like the ones we saw earlier. So what do we do? So initially, so this is uh, bad subset of m and j bad. So So what do we initially do? Initially, we assume that there are no bad rows, and we're going to find bad rows one by one. And what's the definition of a bad row? It's any row where this min entropy condition is not satisfied. So we have this min entropy condition which is not satisfied. So we say that while there exists some I which is outside the current set of bad rows, okay, such that if you look at the h infinity, so we'll also set we also need to set what are the values of the bad rows, the coordinate j bad to something. So initially j bad is empty, right? This is also free because there's no bad row, but iteratively we'll fix these values j bad such that, so we look for an yet and so we look for a currently unrevealed row. So that's a row which is m minus pi. It says that if you look at the mean entropy of ji conditioned, so we are always conditioning on, so we are sampling from the neighborhood of x. These vectors j come from the neighborhood of x, so we are always conditioning on x. So I'm not writing that conditioning anymore, but it's always there. So conditioned on this neighborhood of x, and the current set of uh, so we only sample. So initially we are looking at the entire neighborhood of x, but so far but by doing this iterative algorithm we have identified some bad rows, and we have fixed those bad rows to some particular values j tilde. So let me call this j tilde. So j tilde of bad. So condition on these two things. So what does it mean? So maybe I've identified J1 to be, so J1 is this unique position where row X1 and row Y1 of Alice and Bob could potentially differ. Need not differ, but if they differ, they only differ in J1. Maybe I've set J1 to be 1. So I now look at the neighborhood of X for only tuples J1 to Jm where J1 is 1. So j bad is like some fixed value. So this is some fixed value in n to the bad. Okay. So now I look at this particular mean entropy, and if it is smaller than log n minus tau, I add it to the set of bad rows. If this is log n minus tau, so I'll just make space by shrinking this. Okay. So if this is the case, so this is the condition for the while loop. If this is the case, then first thing we do is that um, we need to find out what to set ji to be. So I is now a new bad row. So we'll add it to the set of bad rows. But before we do that, we need to figure out j tilde of I. Okay. So to do that, let's just use this definition. So this says that, so let me do this calculation here. Since h infinity of ji, given all these things, x and j bad equals j tilde bad, whatever, is strictly smaller than, okay, so this is strictly smaller than log n minus tau. What does it mean? So this means that by just this definition of min entropy, so this means that the there exists. So what does it mean? So this means that there exists a particular ji in n such that probability ji is equal to, okay, sorry, j tilde I, which is a particular value. So ji is a random variable. So probability that this random variable that we get by sampling those neighbors of x where j bad is equal to j tilde bad, if you look at the probability of this being this particular value j tilde I, condition on all these things, it's going to be strictly larger than 1 over 2 to the log n minus tau. This is from the contrapositive of the earlier thing. So we said that if the min entropy was at least log n minus tau, then we would get that probability of ji is j tilde I for any j tilde I is at most 1 over 2 to the log n minus tau. Since it is the mean entropy is not at least log n minus tau, it's strictly smaller than this. There must be some so so this is what I'm saying. So I'm saying, claiming that if h infinity of x is strictly smaller than k, by this condition where we know that if h infinity of x is at least k, all of the x's would have probability at most this much, because it is not true. If because h infinity of x is smaller than that, we get that there exists some x in support of x, such that probability of x being x is strictly greater than 1 over 2 to the k. So if mean entropy was large, all of these probabilities would be at most 1 over 2 to the k. But since mean entropy is not large, there should be something that violates this constraint. And so there is some x where this probability is strictly larger than 1 over 2 to the k. You can convince yourself by also deriving it directly. But this is intuitively, this is just the contrapositive of what mean entropy means. Okay. So by applying that logic here, so since h infinity is strictly smaller than log n minus tau, there must be some particular value j tilde, so some value which appears quite frequently. So there is some j tilde I, so that this j I equal to j tilde I is at least 1 over 2 to the log n minus tau. Okay. So then we find that j tilde I. So j tilde I so is a value such that probability of ji equal to j tilde I given all this is at least this much. So this is a value which witnesses this drop in mean entropy. So we fix j tilde I to be this one, ji to be j tilde I, and we then add I to the set of bad rows. So bad rows is updated to be bad rows union I. Okay. And when you terminate, when this process converges, so once this while loop completes, you can see that every row in I m minus bad would satisfy this condition, right? But because if there is even one I that does not satisfy this condition outside bad, then this loop would still run. So when the process terminates, like in all these kind of cleanup algorithms, we would have one of these conditions for free. The only thing that we need to show is that the number of times this loop runs is at most m over tau. Okay. So for this, we will use a potential argument. We'll say that whenever you identify a bad row that accounts for tau bits of information, and the total amount of information revealed on all these coordinates was m. Hence, the total number of bad rows can only be m over tau. So every time you fix a bad row, you're taking away tau bits of information, and there were m bits of information initially. By a potential argument, you get that every step of this algorithm, the potential decreases by tau. It was initially m. It cannot go below 0, so the number of times this algorithm would run is at most m by tau. Okay, so now it's just figuring out this right potential, and that's not too hard. That is just saying, that's just translating the earlier intuition into a formal argument. So what am I saying? So I'm saying that, okay, so if you look at the coordinates j sampled uniformly at random, but I don't look at the bad rows, I look at every row, so this is like j was initially m coordinates, but now I currently drop the currently identified bad rows and conditioned on. So while we are learning this loop, we are thinking of a particular matrix x. We are sampling this j from the neighborhood of this particular matrix x, and by the the algorithm that we design, we know that the bad rows are going to be already fixed to be, so we only sample those j's where the bad rows are fixed to this particular value j tilde bad, where j tilde bad is some value which witnesses the loss in mean entropy. So we know that. So what are we going to argue? So we know that initially there were m bits of information that were revealed about the entire set J, but now we have found some cardinality bad many bad rows, and each of them should take away tau bits of information. So the mean entropy in this thing, actually, yeah, here we'll we can even, yeah. So the mean entropy of this thing would at least be, so initially what is the mean entropy? Uh, Initially it is like something like at m log n minus m. Here we would scale it appropriately. So what is it? It's going to be m minus bad times log n minus m. So we in it. So why is that? So how many coordinates do we have? Uh, it was, so in here we are not looking at all the coordinates, right? We're only looking at these many coordinates, right? So in this restricted universe, the maximum possible mean entropy of these things is log n. Okay, but we know that we don't have all of these things. Initially, we only had a 2 to the minus m fraction of these things, so they have already lost minus m bits of information. But uh, so initially when bad was empty, we lost m bits of information. But when bad is non-empty, it should not be minus m anymore, right? For every bad row that we identified, that bad row accounted for tau bits of information. So it's not minus m exactly. We gain back for every bad row that we've left out. So that's not accounting for here, right? So we are not counting the information in the bad rows. So we are taking away these bad rows, and this minus m included all those bad rows also. So then we should add back bad times tau, right? So here's the thing. Initially, like, okay, so so for example, when bad equal to phi, bad is empty initially, like this is when the first run of the while loop. What happens? What is this condition saying? It is saying that h infinity of this vector j conditioned on x is at least m log n minus m. And this was the average degree condition that we derived, that we knew that for every x there were these many vectors j that were adjacent to it. Now what I'm saying is that, okay, once you identify a bad row, we are not looking at this universe, we are looking at a restricted universe. We are only considering m minus 1 coordinates. So this drops to m minus 1 log n, and the amount of information I say should not be minus m, because minus m was on all these rows 1 to m, but now we have decided the first row is a bad row and we have chucked it out, and that bad row amounted for tau bits of information. So the remaining information in rows 2 to m should not be minus m, but it should be minus m minus tau. Okay, so when bad equal to 1, we want this to be minus m plus tau. When bad equals 2, we would say tau tau. So for every bad row that we identify, we gain tau bits on the, we account for tau bits. Okay, and proving this is just by definition of mean entropy, and the fact that the j tilde I that we fix for j bad satisfies this. Okay, and if we maintain this invariant, we can see that this mean entropy is, it can never be smaller than 0. Okay, so then we get that m is like cardinality of bad. So in the worst case, the cardinality of bad is at most m by tau. Okay, so this is like the earlier pruning argument. Yeah, but now I'd like to, okay, so I've already taken some time over the limit. So I'd like to conclude by saying that this is not going to cut for us. because now we are not only conditioning on x, but we are conditioning on these bad coordinates being this particular value j tilde bad. But what if, so we know that okay, we know that j tilde bad has some large probability, but it's not still large enough. By conditioning on these events, we could like reveal a lot of information to Alice and Bob. Okay, so we'll talk about more on this issue in the next lecture, and yeah, so I'll stop here. Are there any questions?